Hello everyone, welcome to the 11th session of quantum field theory. Today we're finally at the point to talk about perturbative interactions. The reason they are called perturbative interactions is because these interactions are smaller compared to the background free field solution. So we already dealt with quantization of the free field. When I'm telling quantization, I'm basically saying how to express the fields in terms of creation and annihilation operators. And that's basically quantization. So when we say we quantize the free fields, we're just able to write them down as creation and annihilation operator, which was basically showing their motion in a space-time. So let me write down the Lagrangian of the complex Klein-Gordon minus m squared phi star. So this was for a charge, a spinless particle, and we also talk about fermions that are described by Dirac Lagrangian. And the fermions are a spin 1/2 particles, or they are a spinner. So we found the free field solution. So what were these solutions? They were the eigenstates of the free Hamiltonian. So we were basically trying to see if the Hamiltonian can be expressed as something that multiply the number of particles in each frequency or each momentum mode, and then the whole energy is just sum of the energy of each particle. So that was the deal with the free fields. And now we are ready to add interaction, but we want to add a small interaction into the free fields in order to be able to approximate the solution, because we know if we are adding nonlinear terms, it's not just easy to find a solution like the free field. So let's say our Lagrangian is equal to the Lagrangian of the free fields. It could be one field, can be several fields, and also you have this interaction Lagrangian, and this interaction Lagrangian is somehow smaller than the free Lagrangian. So I can say my field then can be approximated into a free solution plus some perturbative interactions, and this is how we can approach several theories such as quantum electrodynamic, or how the electrons and, for example, photons interact with each other. So now there are several possibilities about this interaction Lagrangian. We talk about these kind of problems in the first sessions, that, for example, Lagrangian is a functional of the field, right? So there are several possibilities. Lagrangian can be only the functional of the field, or the Lagrangian of interaction can be a function of field plus the derivative of the field, or the Lagrangian of the interaction can be only functional of the derivative of the field. And now the question is, which one is basically what we are looking at? And I can say these two are rejected, and the first one is the one that we are looking at. The Lagrangian of the interaction should be only the function of the field, not the derivative of the field. But what is the reason? What is the reason to choose this kind of interaction? Because we are only trying to limit ourselves to the Lagrangian that are the minus of the Hamiltonian. So the Hamiltonian of interaction is only minus of the Lagrangian, and you only have this situation when you don't have any kind of conjugate momentum. In the other words, the Lagrangian derivative with respect to the derivative of the field is equal to 0. So what is the conclusion is that if we have this type of Hamiltonian, then the momentum conjugate that I define for the field phi in the situation where I have interaction plus free solution. So imagine this pi is the derivative of Lagrangian with respect to the derivative of the field. But imagine this pi is representing our momentum. So in the situation where we have interaction plus free solution, this is exactly equal to the momentum of the field phi, but only in the free solution. So imagine these two momentums or conjugate momentums of the phi are equal. And this is important because what we are trying to look is to This is important because we want to define this commutation relationship between phi of x and then pi phi of x. And this was equal to delta 3 of x minus y. So on the other hand, I want to say that if we are only having interactions that are not function of the derivative of the field, then we're going to satisfy the same quantization or commutation relationship between a field and the conjugate momentum of the field. And this is only happening when there is no explicit dependence on the derivative of the field in the interaction Lagrangian. So I can then say, if I have a Lagrangian that has two terms, free and interaction Lagrangian, if I take the interaction to 0, my answers or solutions should go to the free solution. And this is the kind of approximation that we can choose. So the Lagrangian was equal to the derivative of the field Well, let me only write down the real field because for some reason I just want to deal with these powers. I want to talk about these powers, so I'm trying to not to use phi star, but the concept is the same. So I want to say that now I'm using the real valued Klein-Gordon field here. So this is the free Lagrangian. And one can say, then I can have higher order terms. I can have higher order terms. And these are called interactions. If there is no other field is involved, then you have self-interaction. So the field is kind of interacting with itself. Mass, even this term here, is like a kind of self-interaction, but you can kind of integrate it into the free solutions or how the particle move, because basically mass is inertia. It's something about how the particles are moving. But anyway, self-interactions are more sophisticated interactions when the particle, for example, can see the value of the particle itself. So the particle is scattering itself. But we're going to go into the detail of it. Now we want to see what is the meaning of each term. What is the meaning of this free term? And what is the meaning of these self-interaction terms in terms of creation and annihilation operator? So again, for reminder, all the quantum field or all quantum mechanics was something like that. You have initial state, you have a final state, and then you have the Hamiltonian in time, in between sandwich. And the idea is that you can expand this exponential in terms of identity operator. So this is going to be identity plus IHT plus IHT squared divided by 2 factorial, and the other terms acting on the initial state. So we basically have different powers of Hamiltonian. So Hamiltonian is encoding what happens in terms of creation and annihilation, right? Because the field have that information. The field creates, annihilates. So the Hamiltonian also creates, annihilates, because Hamiltonian is basically what? Phi squared, the derivative of phi. Phi, any power of phi is similar to creation and annihilation, but mixing those terms. But I'm just saying that the Hamiltonian is just repeating itself to the initial state. So the Hamiltonian encodes the dynamic, but the dynamic is encoded into the field itself. So the idea is now to see what is the meaning of each of these terms and what extra terms we can add as interaction, or what can we add into the Hamiltonian that makes sense so it doesn't violate certain symmetries that we really like about. Okay, so let's say I'm starting with the next possible integer, power of 3 of phi. So I would say Hamiltonian, or Hamiltonian and Lagrangian can be interchanged with respect to each other. I mean, they're the same thing. But let's say the Lagrangian of the field phi is equal to the free Lagrangian. And then I'm going to add some term here that I call it G phi 3, right? G phi 3. And why not? We want to see whether this kind of interaction is allowed. And again, 3 is the next integer after 2. Well, we can simply reason that this term is not a suitable term because it violates Z2 symmetry. So in general, Zn symmetry is when you have a field and then you can transform it into basically n division of the 2 pi in a complex plane. So basically imagine that you have a field value here, and then this field value can rotate into a circle that has the same magnitude, but they are, distinct value of the field, but they all have the same magnitude. So this is just basically some form of mathematics, but I want to say one form of this is Z2, which Z2 is just basically flip the sign of the field. So if you have a field here, if the value of your field is something like that, then the Z2 transformation is going to flip into the minus phi. So we are just basically taking phi and turn it into minus phi. Or if the value of the field is, let's say, 10, you can say it's minus 10. So just flipping the value of the field. But that shouldn't really change your physics, right? That shouldn't change your anything regarding to Lagrangian or Hamiltonian. But this term here, because it's an odd power of phi, is not invariant under this transformation. So G phi 3 is going to be minus G phi 3. So in the Hamiltonian, you are going to flip the sign of the energy. So you're going to have negative energy. And okay, so this violates some very trivial symmetry, I think, Z2. The other field had respecting this symmetry. So we cannot have this term. You cannot have this G phi 3. It's just because it violates the energy in terms of flipping the value of the field. But now let's go to the next possible power. So in general, you can say odd power is not something that you want. So 3, 5, 7, those are the interactions that you don't think they make sense because they change your physics. So now the next one is always going to write down these free parts. Now imagine you have something like that, lambda over 454. And this is a kind of reasonable interaction. But I want to say that this is the maximum that you can have. You cannot go further than that. It's because your space-time is 4-dimensional. So now it's the time to talk about dimensional analysis. It's time to talk about dimensional analysis because that's something that tells us what kind of interactions is not allowed, because we want to have a basically renormalizable theory, or a good behavior theory that behaves good. So imagine that I have the action. So what was the action? The action was the integral of the Lagrangian density over d4x, right? And we talk about it, the action is dimensionless, right? So the Lagrangian density, the dimension of Lagrangian density, should be the minus 4 power of length, or x. I don't know how to write that in terms of the correct language of dimensional analysis. I wasn't really actually good that much when I started my physics undergrad, but in general, you can say the dimension of the Lagrangian should be the inverse of the dimension of this volume of a space-time. And so we have the 4-dimensional space-time, then this is how it should be. Now we go to the Lagrangian density and try to see what's the dimension of phi, what's the dimension of lambda. And so the dimension of phi can be explained by the first term. So imagine the first term is the derivative of the field, right? The other term is the mass squared, phi squared, and the other one is... So we say this should be equal to x minus 4, the dimension of it. So sorry, I think I'm going to write down some mathematical inaccurate expression, but just forgive me. So anyway, so the derivative of the field is the bringing two length dimension on the denominator. So basically the first term dimension is the dimension of phi squared over the dimension of length squared is equal to the dimension of length to the power of minus 4. Then you can conclude easily that phi dimension is equal to the dimension of x to the power of minus 1, or phi is the inverse of length. Now I want to find the relationship between length and mass, and that's, du Broglie relationship, but we don't know that, but we can easily see that again. So m squared phi squared dimension should be equal to x minus 4 dimension. So we already say phi is x minus 1, so m squared x minus 2 is equal to x minus 4. So m squared is equal to x minus 2, and then the dimension, actually. So the dimension of m, or mass, is x, the dimension of x minus 1. So interesting, mass and phi have the same dimension in this case. Then it's easy to see that the dimension of the lambda, in this case, should be 1, or dimensionless in this case, because you basically want phi 4 and lambda be dimension, or having phi 4, lambda be x minus 4, and phi is already x minus 1. So lambda is dimensionless. Okay, good. But let's see in general, when we have a n-dimensional spacetime, what should we do? When we have an n-dimensional spacetime, then the derivative of phi should be proportional to x to the power of minus n, right? So then, in that case, phi squared divided by x squared is equal to x to the power of minus n. Then phi squared dimension would be the dimension of x to the power of minus n plus 2, right? And then I have m squared phi squared dimension is equal to the dimension of x to the minus n And then again, using the term here, I put phi squared as m squared minus x to the minus n plus 2 to x minus n. So then again, I can conclude here easily that m dimension is x minus 1. That's interesting because independent of what dimension of a spacetime we choose, m is always proportional to the inverse of length, and that's the Broglie relationship. It's independent of the dimension of a spacetime. So that's very exciting here. So now you say that lambda phi 4 dimension should be the dimension of x minus n, and then phi 4, the dimension of phi 4 is going to be the dimension of x minus n plus 2 to the power of 2 is equal to the dimension of x minus n. Then lambda dimension of x minus 2n plus 4 is equal to minus x to the power of minus n, and then the dimension of lambda is equal to dimension of x plus 2n minus 4 minus n, which is equal to n minus 4 is the dimension of lambda. So interesting, because now we have the generalized dimension of the coupling constant. So if n is greater than 4, then the lambda would have the dimension of mass to the power of something. I can just show it with n. And if you have a coupling constant and have some power of n, then the final cross sections of your theory have a cutoff dependency. It's not a renormalizable theory, but we will talk about this in the renormalization section. Now we would like to see what is the meaning of these interaction terms. So we have the free. And if we acted on vacuum, then what is the meaning? Well, we say, let's talk about phi squared. Let's say phi squared. And we already know how to expand phi in terms of creation and annihilation operator. I'm just going to write down the integral over momentums. So now I have 4 terms here. I have a dagger, p prime. Then I have a dagger, a p prime, plus a dagger, p prime, plus a p prime. They act on vacuum. So what is the meaning of them? So the first term here has 2 creation. So it creates 2 particles with momentum p and p prime. So now this is the first time we're going to show some Feynman diagram. So the meaning of it is that at point x, so imagine I'm talking about phi squared at point x. At point x, that creates 2 particles with momentum p and p prime. So this is p, and let's use another color. This is p prime. So at one point creates p and p prime. What about the last term? The last term is the opposite. It annihilates p and p prime. And now it adds these 2. So if we put these 2 together, you basically see it's nothing is happening. Nothing is happening because this is a background creation. This is the background annihilation. And so when you add them, any point of a space annihilates and create with the same rate. So then, you know, the fluctuation is not net fluctuation. Nothing is really coming out. But the other terms are important. These are called propagators. So these are creation, annihilation on the background. These are called fluctuation, creation, but the next term, but these middle terms are propagators. So they create and annihilate, but with p and p prime. So what does it mean? It means that if I have a point x, the first term, let's say, creates p, but annihilates. Let's say p is the first one, and p prime is the second one. Oh, let me choose the consistent color. So this is p. The other term is the opposite. So this is p prime, and this is p. And then we add these 2. We're talking about propagators. These terms are responsible to just move the particle from, you know, one point to another point. So just want to say that now if we add all of these possibilities together, there are 2 terms that creates 2 particles, annihilates 2 particles. But this term is like a form of a scattering. I don't know if you can see what is the scattering. The scattering is that you have something goes in, let's say with parameter p, and something comes out as parameter p prime. And this is the whole point about quantum mechanics. You want to see these scattering probabilities or scattering, you know, numbers, amplitudes. We call them amplitudes. So they do that. And the meaning of these Feynman diagrams are exactly like this. A Feynman diagram represents a process happens at one point of space-time in different momentums. And Feynman diagrams are connection of these processes together. You will see that these processes, for example, should have like a tree structure or loop structure, or you have a free background solution. So it's still early, but we will go definitely into more detail. But this is not a complicated thing. You can just see how this is the meaning of it. Now you have phi 4. Imagine now I'm going to talk about phi 4 term here. So I have a phi 4. So I have a phi 4 term. So I have a dagger, a dagger, a dagger. I'm not going to write down all of them. But imagine p, p prime, p double prime, p triple prime. And then you have so many terms here. And then you have the last term. Again, p, p prime. So it has a similar meaning, but this time it's just more is going into that. This creates 4 particles and then annihilate the exact same particles with the same momentum. So on average, you see nothing is happening in these processes, but there are interaction terms here, and these interaction terms are kind of now they're like this. For example, you can have the terms like that: a dagger, a dagger, a, something like that, or a dagger, a. All the terms in between, they represent different scatterings. So let's say p, p prime, p double prime, p. And now we are talking about these 3 diagrams. Something interesting is that phi 3, for example, that we say it's not allowed because it violates the Z2 symmetry, is something good to represent, let's say, weak decays, because it represents decay. So for the phi 3, we have the similar creation and annihilation terms. So you create and annihilate 3 particles, but you're also allowing to 1 particle to goes in and decays into 2 particles, or the other processes. 2 particles can come in and 1 particle goes out. So it's not all about decay. You know, any decay also have the opposite processes, but I'm just saying that this can represent a decay when 1 particle is split into 2 distinct parts. 1 particle is split into 2 identical particles and vice versa. So this is what phi 3 is doing. Another example for the interaction is QED. So the Lagrangian of the QED is equal to the Lagrangian of the free Dirac field plus the Lagrangian of the free electromagnetic field, or the vector potential, and then the Lagrangian for the interaction. So the first term, we know what it is. I'm tired of repeating it. And then the second term is also interesting. It's a pure gauge field, or it's a non-interacting. I mean, the free form of it is like that, or maybe like this. So F mu nu is the electromagnetic tensor, and this represents the whole free electromagnetic wave in different gauge. So I mean, we later talk about how to quantize this, how to quantize that free electromagnetic wave in the functional method, in the path integral method, because that's more straightforward there. It's not really straightforward to prove it in this version of quantization, but the interaction term is interesting. So there is a coupling constant here, E, and then you have psi bar, and then you have psi, and then you have psi, and then you have gamma mu, and then a mu. So this is what couples the electromagnetic field to a fermion. This is why the electron can see the photon. This is why. And we can kind of absorb this term into the first term and define covariant derivative. We can, and that's how we can kind of, again, if we absorb the last term here into the first term, we can like have 2 free Lagrangian, because this red one is free. And if we add this term into this term and define covariant derivative, then we are talking about a free fermionic field, but with the background of the geometry of the electromagnetic wave. Maybe it's right now, it's not a proper time to talk about it, but I can write down the Lagrangian like this. So the first term would be psi bar psi, but now instead of regular derivative, I'm going to use this term, gamma mu minus I e a mu. So that's how I'm absorbing that term, minus m to psi. And I can call this one the d mu, or covariant derivative. And then I say I only have 2 kind of free field. But one of these fields is a gauge of the other one. So when I'm transforming my fermion, for example, psi of x goes to psi of x into an exponential term, it's a local phase transformation, then my electromagnetic wave should transform like this in order to keep this term invariant. Sorry, I need to have a... So now if I transform a field with an arbitrary function alpha, I should also use that alpha function to move my electromagnetic field, because that's a kind of constraint on how these systems are interacting. But it's very beautiful. It's a concept of gauge field. We're going to get to that. But it is just, an introduction here. So this is one type of interaction we're dealing with, fermionic interaction with the electromagnetic wave. The last one is the Yukawa theory. So imagine I say the Lagrangian of the free Dirac field, now plus the Lagrangian of free Klein-Gordon field, plus some interaction term. And this is the Yukawa theory. It's similar to how proton and neutron were interacting with each other. Nowadays, we know that the picture is more complicated because pions are not basically a scalar particle, but so you can have the free Lagrangian, free Klein-Gordon, and then you can define this term here. So like some coupling constant, psi bar, psi, phi. So this is similar to phi 3, but it is allowed because there is not only one field here. So we still have 3 fields here. 1, 2, 3. But 2 of them are fermion, and the one is sandwiched between is a scalar field. And now we can see the type of processes like that. So what is the meaning of that term? The meaning of this term is that, so this is when psi comes, or particle comes on A. The other one represent particle that goes out, and then we have the absorption or emission of the Klein-Gordon particle. And this is the basis of the interaction. So what is interaction? Interaction is basically a fermion that then absorbs something. It could be a scalar particle, it could be a photon, and then that fermion goes out, kind of absorbing. And then you can also looking at the emission, very similar to that. So this is called Yukawa theory and Yukawa potential. It's a famous way to estimate the mass of the pion. So at that time, I think it was in the 1930s, people were trying to think how proton and neutron are kind of bounded, how proton and neutrons are sticking together inside of the nuclei. So the idea was that there is a potential between them, but we don't know what is the mass of this force carrier, but they know the estimation of the separation between these two. So they got a potential out of this characteristic length, and then that length was translated into a mass, and the mass was close to the mass of pion. It was before it was discovered, and pion and muon at that time were eventually discovered in the same mass range. First they made a mistake between these two, but later on it was obvious that one of them is a lepton, the other one is a hadron. The other one is a different, distinct thing. But now we just have the summary of the session. So what we learned was that we had all these free Hamiltonians, and then we said what if we add some perturbative interaction to them, what conditions it should have, and we said it should only be a functional of the field, not the derivative of the field, because we want to hold the same commutation algebra. So we want to have the same basically momentum, same corresponding conjugate momentum of the field. So we don't want to have any explicit dependence of the derivative of the field. And then we gave an example of how we can have higher order terms. So we can only have even powers of the phi. We already talked why we can't have phi 3 because it violates Z2 symmetry. And then we talk about dimensional analysis, and then the importance of the dimension of a spacetime in the context of renormalization. So if we have a 4-dimensional of a spacetime, the interactions up to phi 4 is allowed, then phi 6, phi 8 are not allowed. It depends on the dimension of a spacetime. If we have an n dimension of a spacetime, then we can only have n-4 up to the n-4 is setting a threshold for the renormalizable theory. And then we talk about the meaning of this phi squared, phi cube. These are like different interactions, different creation and annihilation. On the other hand, any complicated thing is only translated to the language of creation and annihilation. And it's the whole point of quantum mechanics. It's not a complicated thing happening in one point of a spacetime. Something goes in, something comes out, and you want to see what's the probability. So we have different interactions. Probably the most important one for the 20th century is this QED. It's the most accurate quantum field theory predictions comes out of QED, when we are measuring the different properties of the electron, such as charge of the electron and the magnetic moment of the electron up to the very high number of digits. And we talk about this covariant derivative, and then we talk about this Yukawa theory. And then we're going to calculate them. All of them, we're going to calculate them. And in the next session, we're going to talk about Dyson method of getting the evolution matrix. And then we start to calculate Feynman diagrams. And then after they are done, we go to another method called functional method or path integral. With the path integral, it's similar to calculating the partition function in thermodynamics. We can calculate the propagators of interactive theories. So we still have a long way to go, and but we are going slow, and we are trying to go deep into the concept, and it's very fun. So thank you so much for following this channel, and I will see you in the next session. Thank you so much.